There we go. All right, so the primary area that I work in, for those that don't know me that well, is really the large-scale data management of things. And as the technology's been shifting the last several years, it really started with the introduction of Flash becoming affordable, but has really accelerated in the last few years. What exactly counted as storage infrastructure versus what people wanted to use as memory infrastructure has really started to blur, and I've been trying to figure out where is that dividing line, and I've discovered some opportunities I think that we as a community should look at trying to address, because it's going to give us some advantages that I'll go through. In terms of the kinds of things that I work on, I really look at very much the large scale up. So these will be your like large weather simulations or any of the other large bulk synchronous parallel kinds of applications. I don't do that much work with the large scale data analytics, but it's an area that I have enough exposure to that I understand a lot of the general characteristics that those applications require. And the things that I've come to understand is that there's really a complete disconnect in terms of the hardware architecture between what the scale up applications really need and what the scale out applications really need in order to work most efficiently. And this talk's going to go through what I see as a potential way to bridge those two so that we can have a single platform that ends up addressing both workloads essentially optimally. The technology that I've run across is called persistent memory. The only product on the market today is the unfortunately poorly named Optane chips from Intel. This is different from their other Optane, which were the storage accelerator devices, but these are their persistent memory devices that they live on the memory bus. Within the CPU, they actually have a separate memory controller, since these do have different performance characteristics than regular DRAM. And they offer a persistent memory, which is cheaper per capacity than traditional DRAM would be, and also offers the persistence. The non-volatile memory over Express, the NVMe Express devices, those are generally lots of parallel flash that are put onto the PCI Express bus, and they offer very high bandwidth, but still not as good as the persistent memory, since it's on a slower bus and it's using slower technology. But it's also an expensive way, and people have been starting to take advantage of it. And I think persistent memory may take us and push us over the hump to something that truly can be a technology that both the applications people, in terms of needing additional memory, and storage people looking for additional ways to store things securely, can really take advantage of. So the real technology shift, I think, started in 2012 with the introduction of burst buffers. This really went back to earlier work that was happening at Sandia as early as 1996. And the idea there was really, can we use additional RAM or other sorts of memory resources within the compute area to stage data for other compute tasks? And flash memory gave us an opportunity to have higher capacity at lower cost that was also nearby, but it was still too expensive to take over for disk for our main scratch space. So that's where burst buffers came in. I still consider that a transitional technology, that eventually disk is going to be pushed to a lower tier and flash is going to be our only scratch storage space. And I'll go into that here in a little bit. So the quad level cell flash, that's really been the game changer in terms of flash versus disk. And the difference there is that it's maybe 10% difference in price or capacity compared to what disks are. And even though the write endurance isn't that great, if we look at the lifetime of the machine that they're attached to and the amount of use that they get, that level of write endurance that we would potentially want really doesn't matter that much, because we're not going to hit those limits. And because the performance is so much better, we can actually buy less of it, because we've been buying disk based off of the bandwidth rather than a capacity, and have had excess capacity compared to our needs for many years. So this gives us a way to really end up with a much faster storage capability, but this persistent memory piece gives us an even faster tier that's closer to the memory. So this dividing line of what actually we should treat as memory and what we should treat as storage is not really clear anymore. In terms of the memory side, the thing that we're trying to see if we can switch to with, as far as Sandia's machines go, is how much high bandwidth memory on package can we afford? And the answer is not quite enough, unfortunately. We would like to be able to move from having any DRAM to having all high bandwidth memory on package because of the performance benefits, but the price is still a little bit out of reach. There have been other sorts of approaches for trying to do memory that is just distributed throughout the machine so that we can try to get better use out of it, such as HPE's the machine, but that doesn't have the same performance because you got to go across the networks. And persistent memory, I think, is going to be something that will give us the additional capacity that we need to be able to afford enough high bandwidth memory, and at the same time gives us a flexible resource that we can use for other purposes. The thing that's really kind of pushed on this is that what we've realized in our own testing internally is that the SATA bus that you would normally attach an SSD to is much slower than the network. So using storage resources or RAM on a node across the network is actually much faster than going across the SATA bus. So we can eliminate that as a potential resource. So then we look at NVMe devices, and those are really expensive though, and that's been part of the problem with trying to deploy large quantities of them. And their advantage, while great from a performance standpoint, it's still slower than persistent memory, and they're an additional device off a different bus, and we have a different way of accessing them that's really very storage focused. So if we want to look at how memory and storage really split apart, how they look at the different technologies that are there, memory kind of has this hierarchy of registers, then the cache, then the high bandwidth on package memory, then anything off the memory bus. And storage kind of starts at that memory bus and then goes to NVMe, then remote storage, then disk or tape. And the question is that if we have persistent memory, does it have to work as memory, or does it have to work as storage, or should this be something that can work as both depending on how it works better? Part of what we need to understand if we're going to make a decision about this is what are the attributes of something that is used as storage and what's the attributes of something that's used as memory. And in talking with applications people and other storage people beyond myself, these are the kinds of things that people have described to me as what they consider as either storage or memory. So for storage, we look at things that are, we want to have data that lives beyond the application execution. There needs to be some sort of encoding around the data so that it's easier for somebody else to read later. For example, the ADIOS or HDF5 formatting puts additional annotation around the data so that you can read that arbitrarily without actually having to know what the encoding format is. And there's also something about the architectural assumption. So for example, big endian versus little endian is something that will be encoded into the format so we know how to deal with it. And the last one is probably the most important one historically, and that is whenever dealing with something that was considered a storage device, we considered it slow, and therefore we could justify doing a lot of different operations to be able to make the data access faster. That last assumption is the one that is really in the most trouble today. In terms of memory, if somebody looks at it from an applications person's perspective, data only lives as long as the application, because when the application exits, the memory's cleared and it's gone. The data is also stored as densely as possible because they want to be able to fit as much into a cache line as possible. And everything that's needed to understand those bits sequentially is encoded into the application so that additional annotation around the data is not really required. The reading and writing environments are identical. So there's not really a difference in how they work. And the last one is that reading and writing is fast. So there's not an assumption of I shouldn't read or write something because it's going to take a long time. It's more a matter of if I need to write something, I write it. If I need to read it, I read it. There's no real consideration of the performance of that operation. So if we look at persistent memory, since it's on that memory bus and can fit on either storage or memory, the question is it slow memory or is it fast storage? We don't really have a good answer for that. Second question, does persistence matter? Garth Gibson several years ago at a workshop stood up and declared that the least interesting feature of Flash was the persistence. And that, in my opinion, has turned out to be probably, at least in this area, absolutely true. And if it's across the fast interconnect, does it matter if it's persistent or not? Does it matter if it's memory or a storage device? And the answer is probably not. And does it have to be natively byte addressable for something to be considered memory or storage? And I would offer that since we can put any sort of API in front of a device, I don't think there's really any difference between something having a native byte addressable interface and something that has an API that offers a byte addressable interface. There is different performance characteristics that may happen behind the scenes, but it doesn't change the programming interface. So if we want to look at something, if we want to look at these 4 different questions here, if we want to organize data for highest density, that is something that's generally done for a memory usage. If we want to organize data in an archive or long-term reuse format, that's usually something that we do for a storage purpose. Now, the next 2 really are kind of interesting questions. So if an application writes its checkpoint using a raw memory dump, is it using the storage, for example, disk? Is it using it as memory or is it using it as storage? And that's one that's really not clear. They may claim that they're using it as storage, but the reality is that the way that data is put onto disk is a way that only an in-memory version or use of that data can actually understand it effectively. And because of that, I would actually argue that that's actually a memory use rather than a storage use. Then the European Center for Medium Range Weather Forecasting, they've gone and done something that really threw a monkey wrench into everything, and that is that they changed how they organize their data so that everything is always stored in a storage format, even when it's being computed on. That way, whenever they pull in something from storage that they want to run regression tests on, they just work on it directly, and they don't actually have to do any format conversions between what the memory image format and what the storage image format would be. This also saves them additional operations and writing things out to storage because they just are always computing on what that storage format would be. So in this case, they've kind of taken a storage view to everything and just assumed that there are places where there's enough performance to be able to make things work. So in that sense, I'm not sure if it's really storage or memory anymore. It's kind of both. So the apps people that I've worked with over the years, they very much see this persistent memory or flash even as slow memory. It's something that they can swap to that is much better performance than disk. So they look at it and say, great, I have extra slow memory capacity. And they want to be able to use CPU load and store instructions, though, so that programming is easy. And that's something that is a little more difficult when it gets to Flash, but that's something that we've kind of built libraries for with doing things like memory mapped files and things like that. But so we've given them ways for that to work. The out-of-core computation is what we actually need as a way to bridge that price gap for the high bandwidth memory. So until we can afford enough high bandwidth on package memory, we're going to need some way to be able to swap out what's being computed on for something that's in a nearby, as faster performance as we can get, but affordable storage location, and then be able to swap in new things to work on. And I think persistent memory may be a good way to do that. For storage people look at the persistent memory as great. I have a place I can write my checkpoint files to basically at memory kind of speed, and I can have the best checkpoint performance possible. They know it's persistent in case of a power loss or a crash, so that they say, wonderful, I now have this resilient place I can store things in. They like to be able to map it directly to storage, but the thing is that it uses memory operations. But again, this is something that is easy enough to handle with a bit of a different API on top. And something that's been done with burst buffers, but that could also be done with persistent memory, is this auto migration. And that is something that we could just extend into this technology as well. So in terms of who wins, is like, should this be a memory technology or should it be a storage technology? These are the kinds of questions that we have to look at, because these are all the different things that we really care about over the long term. Is if we have big machines, the purpose behind them is to run really large-scale compute jobs on them. So whatever the technology needs to be able to support those jobs is really what's required. And if the technology works best to support that as a memory technology, that's what it needs to be. But if it works best to use it as a storage technology, that's what it needs to be. And then we have to look at these other things as well, such as what's easier to program, how do we handle data movement through all these different tiers, because this is yet again another tier. And we also have the workflow and network communication kinds of things to deal with. In terms of the bottom line, the data lifetimes I don't think are interesting. Burst buffers also offer a persistent but node local storage in many cases. For example, like the Summit machine at Oak Ridge had node local NVMe devices and was using that as a burst buffer. So the difference between that and persistent memory, I don't think is meaningful at all. The architectural assumptions, I think, are fairly well standardized at this point, so that we know that how the persistent memory is going to work and what kinds of programming interfaces we think we want if it's a storage device or a memory devices. The data encoding, I think, really might be the only difference that makes anything different between memory and storage. But again, the ECMWF people have really said, I'm not even going to pay attention to that. I'm just going to store things in one format and use it for everything. And because of that, I don't think there's really a dividing line between them anymore, and it's something that we need to really investigate. And I think this is an area that's ripe for research exploitation. So some of the things that the applications people have said is what they really want is to move away from having to learn and use a special I/O API, no matter what it is. And they'd rather just do a mem copy and be able to say, I want to mem copy this data structure to something else that I know is a persistent storage area. And they don't really want to have to do anything much more than that, other than maybe have a flag on there that says, move it to the persistent area. And then they'll be happy, because it's much simpler for them to do. But there's also things that they need to know. For example, is what I'm computing on in the slow memory or the fast memory? And that's something that they're going to have to pay a bit of attention to, but they already do a bit of that with something like the COCOS model, where you have particular locations for your data and your compute areas, like at the GPU or the CPU, and you actually have to execute a command that says move this from this memory space to a different memory space. And that may actually be a no-op depending on your underlying architecture, but it does make the programmer aware of, am I doing something specifically on a potentially slow memory area or a fast memory area? The byte to block translation, that's something that we do already. I don't think we really care about that at all. But the bottom line one that I think is the most important one is, since Intel is the only vendor that currently supports persistent memory in the CPU, when are these other CPU vendors going to step up and start to support it? And I think until we as a community show the applications people and the storage people the advantages that we can gain and the cost savings and the performance benefits we can have, then I don't think we have enough ability to put pressure to say we need these features. If we're going to have some of the other things that we'll have to do is, if we have a mem copy kind of interface, we're going to need some automatic translation unless we're doing an ECMWF setup where we keep everything in a storage format to actually add in all of the additional annotations. And that's something that it's easy enough to do in middleware, but it's something that we'll have to do as a replacement for the mem copy. And if we want to worry about the machine architectures, since these do change over time, for example, if we move from a 64-bit to 128-bit word or something else like that, that changes how the data is laid out, then we need some way to identify these if we don't have that additional annotation there. And we also probably need to work more on the migration side of things. Right now, we have several people throughout the research community have proposed ways to do the data migration, but I don't believe any of those have really been rolled into production in terms of getting off node. I know GPFS has, if they have node local burst buffers to migrate off, but this is really a two-way migration as well, and I think this may end up being a bit more complicated than what they may do. So kind of the bottom line is why we care is that this persistent memory is potentially a hybrid technology that can really give us additional memory when we need it or node local storage when we need it. It gives us a way to be able to take advantage of as much high bandwidth memory as we can until we can afford it. And we can still use NVMe devices on fat nodes, but if we have thin nodes, persistent memory may be our best approach to getting us additional capacity. Kind of go through all this. So the bottom line here is let's do our best to lobby the CPU manufacturer so that we can get something useful out of this, because I think this is something that can give us a single machine that is optimized for both scale up and scale out workloads effectively. So that's my talk.
Thank you very much, Jay. Again, something new. We are learning all the time, so we are waiting for maybe 1-2 questions from the audience. In the meantime, Jay.
Yes.
Since we are talking frontiers here.
Yes.
What do you think would be the effect on performance and the quality of a supercomputer if you imagine that the frontier supercomputer AMD with AMD processors and accelerators would have this persistent memory? Imagine that this scale of machine. It's a huge machine, and suddenly you have what you are talking about.
Right. Right. Frontier has already shifted to, I believe they have an all-flash front-end storage array. I can't remember exactly on that. So that takes the disk out of the equation. So that makes that part of it easier. In terms of the GPU side of things, they still, because the GPUs don't necessarily have enough memory space, are going to need that additional swap space. So this gives them a much higher capacity per node of memory to be able to do the computations that they want. If they want to do large-scale data analytics, they now have a node local storage device that they basically, on job deployment, they can just basically flip a software switch and the hardware ends up becoming a different purpose. And that kind of functionality, I think, will make the machine more broadly useful for a wider range of things, as well as give a lot more data intensity to the fat compute nodes.